Hi, here we discuss about a project fully array Boolean Logic CIM Macro with a self-recycling 10T-SRAM cell for AES Systems. Here, the static random access memory has become one of the most essential building block in modern low power and high speed digital systems such as a portable electronic signal processing unit and encryption engines. Conventional 60 SRAMs and 80 SRAM cells provides a compact designs and fast access, but they suffer from limited noise margins, higher leakage power and additional circuit requirement for logical operations, leading to larger delay and power consumptions also. Here, to address these issues, the recent research explored 90 SRAMs and 10T SRAM designs which improve the stability and reduces leakage, but often lack efficient integrations for logic in memory applications. In this work, we developed a single bit 10T SRAM cells in 45 nanometer CMOS technology and extend it into 8x8 SRAM array. The novelty of this design lies in combining the stable storage with the logical optimization, where the SRAM array is not only used for memory but also used for inbuilt with the OR gate operations, XOR gate operations and AND gate operations without requiring additional dedicated hardware. Okay, so this approaches directly improves the energy efficiency and speed optimizations while minimizing the overhead of extra circuits. We evaluate the designs under the varying supply voltages and measuring delay and power consumptions and observe enhanced write and read stability and reduce dynamic power consumptions and faster logic executions compared with the SRAM's stretchers. And the entire designs was tested using a industry standard simulation platforms with a 45 nanometer CMOS technology to ensure the realistic validation. These results indicate that the proposed 10T SRAMs based on the memory logic array offer a stronger potential for embedded computing systems where both storage and basic Boolean logic operations also needed within the same architecture, so making it highly suitable for portable devices and medical electronics and encryptions accelerators. Okay, so here we verify the work. Okay, so this work, the fully designed for the 10T SRAMs is the main core of this paper, but the application wise it will be using for the AES systems. Okay, but in this paper specifically not only design a 10T SRAM cells, using this 10T SRAM cells they will be designed for the logic gate operations, which means AND gate, OR gate, XOR gate. Okay, this kind of operations. Okay, so commonly the 10T SRAMs it will be interconnected with the two inverter based architectures. So this is one of the inverters and this is another inverters. In between they used for different level of conditions here. Okay, to control the signals. Okay, so it means a CN, RCL and CL and RCN. Okay, so and RCL. Okay, so this kind of things they are used. Okay, so depends upon this prioritized one, so which one we need to high and which one we need to low, depends upon that we can possible to control this SRAMs with using for logic operations. Okay, so here the write line it will be used for writing the data, and bit line BLB is a data input, and power supply and ground it will be additionally connected. Okay, so here this is a read operation mode and this is a write operation mode. Additionally the circuit come with the AND gate operation. So this is a AND gate operation logics and the truth table. Okay, and this is a OR gate logic, OR gate, XOR gate and the IMP logic gates. Okay, so here this logic gates it will be come with this kind of truth tables. Okay, so mostly the truth tables given in the papers it will be not sufficient for the output. Okay, so we modified everything and we'll be get a new truth table, and then we will prove this work in a Tanner EDA at 45 nanometer CMOS technology. Okay, so now we can verify the work. So here this is a first design. So TB 10T SRAM cells. Okay, so here the BL, WL, BLB, CL and CN, RCL, RCN. Okay, so everything it will configured, and this is the architecture design of 10T SRAM cells. Okay, so here you can verify the simulation results, W edit. Okay, so here you can verify the simulation results. So this is a BL and this is a QB and Q and WL and BLB. Okay, so BL it's a complement in the BLB. Okay, so while at the time of WL we are writing the data and as well as reading the data. Okay, so here you can write a 0 here and we write the 1 here. Okay, so at the time of BL data. Okay, so you can verify it in the Q and Q bar. Okay, and the second output is AND operation. Okay, so here this one is the AND operation and this is a mode control signal. The same SRAMs we are used, but the control signals only we are changed here. Okay, now I'll execute the simulation now. Okay, so this is the AND gate operation. Okay, so AND gate operation means the 1 1 in the AB means it will be come with the 1. Okay, and the same for OR gate operation. Okay, so this is for OR gate operation. Okay, so OR gate operations come with the 0 0 means 0, otherwise it will be come with a 1. Okay, and next one is the XOR gate operation. Okay, so this one is the XOR gate. Okay, so XOR gate, it's finding the difference. So 0 1 or 1 0 means it will be come with 1, otherwise it will maintaining a 0. Okay, so here the input it will become with the A and B here. Okay, so and the control signal depends upon the control signal we taken the output. Okay, so additionally we developed the array architecture of SRAM 8x8. Okay, so this is a SRAM 8x8 array architecture. Okay, so this architecture we initiated and it will be generated at 45 nanometer same technology size. Okay, so here I'll execute the simulation part. Okay, so this is a SRAM 8x8 array architecture. Okay, so this is the simulation results, and we can execute this work in a netlist configurations with support of T-Spice. So this is a netlist for your SRAM array architectures, and also we can analyze the temporary folder. Okay, to analyze the simulation outputs. Okay, so example TB XOR operation means, so here we can analyze the MOSFET, and here we can analyze the power results and delay. Okay, so everything will be analyzed, and this comparisons, it will be updated in the comparisons document here. Okay, and finally we written a abstract document for this project. Okay, so here this is abstract, base paper abstract, improvement and proposed title, existing systems, disadvantages and proposed systems. Okay, and related notes with all the circuit truth tables. Okay, so everything it will be proved in the project. Okay, and finally come up with the literature survey and references. Okay, thank you.